Hello, and welcome to this fourth video in a series on nuclear chemistry, aimed at National 4 and National 5 level. Today we're going to deal with half-life, so by the end of this video I'd like you to know what half-life is. What you should already know is that some isotopes of elements are radioactive. That means they undergo nuclear decay. They give off radiation. You've got alpha radiation produced by alpha decay, and alpha particles are helium nuclei. These are released from the nucleus of a radioactive atom and are composed of 2 protons and 2 neutrons. Then you've got beta radiation, which produces beta particles. Beta particles are electrons. Notice these are produced from the nucleus. They're produced when a neutron breaks up to form a proton and an electron. And finally, you've got gamma decay, which is basically a form of electromagnetic radiation. We're going to be mostly interested here in alpha decay and beta decay because these change the isotope from one element to another. Now, this is what makes nuclear chemistry unusual. Normally, atoms don't change from one element to another in other parts of chemistry, but here they do, because the nucleus is changing, particularly the atomic number changes. So alpha decay, for example, decreases the atomic number by 2. And beta decay increases the atomic number by 1, because a neutron turns into a proton, thereby adding to the atomic number. Okay. So let's consider what half-life is. Let's consider a radioactive isotope. And the one I'm going to choose is rhenium-189. That's rhenium with a mass number of 189. Okay, and I'm going to represent an atom of rhenium-189 like that, a red ball. And when rhenium decays, it does this. Your rhenium-189 turns into osmium-189 and releases a beta particle. Notice the mass number hasn't changed because the beta particle has virtually no mass, but the atomic number has gone up by 1. This is osmium-189, and I'm going to represent it like that. Okay, now let's assume we've got a sample of absolutely pure rhenium-189. Okay, that's a pure sample of rhenium-189, 32 atoms of rhenium-189. Now, over time, those rhenium atoms are going to decay. They're going to undergo beta decay and turn into osmium atoms, like that. Now, this is a completely random process. We don't know which atom's going to decay, but every so often one will decay and will turn into osmium. Now, this is going to take some time to do. Okay? Now, the time it takes for half those atoms to decay is called the half-life. So there we have that now. We started with 32 rhenium atoms. Now we've only got 16. So half of them have decayed. The time that's taken is 1 half-life. So that's the time it takes for half a sample of a radioactive material to decay. Now, in the case of rhenium-189, that's a day. That's why I chose rhenium-189, because it has a nice simple half-life to work with. Now, at the end of that first half-life, half the atoms of rhenium are left. Okay, let's now have another half-life. Okay? Now, the rate of decay is going to slow down because you've got fewer rhenium atoms to decay. But at the end of that second half-life, at the end of a second day, you've had 2 half-lives, that's 2 days, and you've only got a quarter of the original sample left. You've only got 8 atoms left there out of the original 32. Okay, a third half-life. Now it's slowing down here because you've got fewer rhenium atoms. Okay, and at the end of your third half-life, that's after 3 days, you've only got an eighth of the original sample left. That's a half of a half. of a half. Okay, one more half-life. There we go. This time we're left with 2 atoms after 4 half-lives. That's 4 days. You've got 1/16 left. That's a half of a half of a half of a half. Okay, so key point, a half-life is the time that it takes for half a sample of radioactive material to decay. Now this will vary from one isotope to another. Okay, so for the next one, we're going to choose a different radioisotope. I'm going to be working with protactinium-228. Again, I've chosen this because it's got a nice simple half-life to work with. Okay, now it undergoes alpha decay, like that. So protactinium atoms turn into actinium atoms. Okay, notice the mass number has gone down by 4 and the atomic number has gone down by 2. Now the half-life for this is 22 hours. Okay, so let's plot a graph. Let's assume we've got a sample of absolutely pure protactinium-228. Okay, and we're going to plot the percentage of protactinium over time. Okay, right at the beginning, after no time, then you've got 100% protactinium. Okay, plot that point there. Now, after one half-life, after 22 hours, you'll have half the sample left. That's 50%. There we go. 22 hours, 50%, plot the point. After a second half-life, so that's 44 hours now, you'll have a half of a half, or a quarter, which is 25%. There we go. 44 hours, 25%. After 66 hours, that's 3 half-lives, you've got a half of a half of a half, or 12.5%. Okay, there we go, 66, 12.5, plot there. And one more, after 88 hours, that's 4 half-lives, 4 lots of 22, you've got 6.25% left. That's half of a half of a half of a half. Okay, there we go. And we'll plot that as a graph. Now that shape of graph is absolutely typical for radioactive decay, so kind of get used to that. So how do we measure the percentage protactinium? Well, we could measure the amount of radiation coming off the sample. The bigger the percentage of protactinium, the more radioactive decay there's going to be, the more alpha particles produced, or beta, okay, and these can be detected using a thing called a Geiger counter. So this counts the number of radioactive particles, maybe per second. And what you get is a graph that looks like that. Same shape. Okay. And this would show a half-life of 44 hours. So we would also be able to say this is not protactinium-228, because we know the half-life of protactinium-228 is 22 hours. So let's go back to protactinium again. We could also look at the mass of protactinium in the sample. Okay, again, that's going to decline over time in exactly the same way with exactly the same half-life. One thing I should emphasize here though, we're talking about the mass of protactinium here, okay? Not the mass of the sample as a whole. Remember, the protactinium is turning into actinium. So protactinium atoms are turning into actinium atoms, and they still weigh not quite as much, but a fair amount. So the total mass of the sample is not the mass of the protactinium. Okay, important things about half-lives. First off, the half-life depends only on which isotope it is. So we've talked about 2 isotopes so far in this video. The protactinium-228 half-life of 22 hours. Nothing can change that, okay? You cannot change the half-life of an isotope. So you can join it up with other elements to make compounds. You can mix it with other things. Won't make any difference to the half-life. You can change the state, melt it, dissolve it, whatever you like. It won't change the half-life. You can heat it up, cool it down, anything you like. It won't change the half-life. Nothing changes the half-life of a radioisotope. And that's going to turn out to be very useful in a later video. One thing I should also emphasize, that the half-lives of different isotopes can be very different from each other. I mean, so far we've seen half-lives of about a day or so, but they can in fact be anything from thousandths of a second right the way through to millions of years. Okay, so summing up. What is half-life? It is the time taken for half the atoms in a sample of a radioactive isotope to decay. And you can track that by measuring radioactive activity over time, using something like a Geiger counter, or measuring the mass of that isotope in the sample over time. The half-life doesn't depend on anything other than which isotope it is. And different isotopes can have very different half-lives. Okay, that's all for now. Thanks for watching. Goodbye.